All right, in chapter 10, we're going to talk about specific chemical reactions, start talking about chemical equations, and as well as we'll also talk a little bit about energy, the types of reactions, how to balance reactions, everything about a chemical reaction. All right. So the first thing is that one of the things that you're going to have to be able to do is to recognize what type of chemical reaction that you are dealing with. There's technically two different types that we'll talk about, but each one has a few different types of reactions. Okay, so the one thing to note is that chemical reactions cause the rearrangement of atoms, but do not cause either the creation or the destruction of atoms. So if you do a reaction with hydrogen and oxygen, your final product is going to have hydrogen or oxygen in it. You're not going to just magically make a chlorine atom or something like that. It's composed of the atoms or the elements that you start with. Also, the amount of matter or the mass is neither created or destroyed. This is called the law of conservation of mass. All right, so if you start with like 8 grams of your compound, at the end of the reaction, you will also have 8 grams of your compound. All right, nothing's going to be created or all destroyed. Okay, so here's just kind of two examples of a chemical reaction. You've got a horseshoe made out of iron on the left side, and then over time it oxidizes in the presence of oxygen to form rust or iron oxide. All right, so technically this reaction will look like iron, which is a solid, plus oxygen. Oxygen is a diatomic molecule. We learned about that. The have no fear of ice cold beer. And you form iron oxide, all right, which is a solid. And remember, I get this formula because oxygen always has a -2 charge. Iron typically has a +3 charge. So that's where this formula is coming about. Okay, you might be saying, well, I don't have 2 irons on this side, and I don't have 3 oxygens here. Well, this is something called balancing the equation, which is something that we will do in this chapter. But for completeness and just to kind of show you, technically, what you would have to do is if you want to balance this equation, this is actually what it's going to look like. All right, and we'll talk about how you do this, but you've got 4 irons on this side, and you have 4 irons on this side, and you have 6 oxygens on this side, and you've got 2 times 3, 6 oxygens on this side. So this kind of tells you it's a 4-to-3 ratio of your starting materials to form twice the amount of your product. Okay, we will talk about balancing, but for right now we're just talking about how you determine a chemical reaction. Things don't create or destroyed. Here's a cake, here's a raw cake, and then when you cook it with the yeast, you probably don't have yeast in the cake, but like the baking soda and stuff like that reacts and you get air inside of it and you cook everything. You're just changing the components, but you're not changing the atoms. You're changing how they're arranged. All right, so this is kind of a, I don't know, a real simple problem just to kind of show you a physical change versus a chemical change. All right, so imagine that we're starting with A. Notice you have green and red atoms hooked to each other. So let's say A is the red and B is the green, and we are in the liquid state. So you show that with an L. All right. Well, which one of these examples between B, C, and D, which one is a chemical change? Which one would you consider a chemical change? Well, it'd be B and C because these are no longer A and B. We have A attached to A and B attached to B. And then here we have A by themselves and B by themselves. So these are chemical changes. This one, D, is in the gas phase. It's your AB, but in the gas phase. Okay, but notice you still have the same atoms. You haven't created any atoms or changed any atoms. Okay, so this is kind of a real simple problem just to kind of show what we're talking about. All right, 10.2, we talk about basically what a chemical reaction is and what are the words that we use or the nomenclature of how to talk about a chemical reaction. Okay, and pretty much everything on the left side, so the arrow is kind of our central point. Everything to the left side is called our reactants. Okay, another term are our starting materials. I'll put SM as starting materials. All right, and the arrow shows what it yields or what it forms, and everything on the right side of the equation are our products. Okay, so basically what it's saying is a chemical reaction represents a statement. When you encounter a chemical reaction, you may find it useful to read as though if it was a sentence. So ammonia and HCl react to produce ammonium chloride. Okay, that's basically how you talk about it. So here the reactants are on the left side of the equation, all right, and then your products are on the right side of the equation, all right. For nonmetals that exist as polyatomic ions, we generally use the molecular formula in equations. So notice these are the diatomic molecules, have no fear of ice cold beer, okay. And then phosphorus as a P4, we really won't deal with that. But this is not something we've learned or something that we're going to have to worry about. They just kind of added it in here. I really want you to know the diatomic molecules. All right, so like if we have, I don't know, magnesium react with oxygen. The element oxygen is O2, and you form magnesium oxide. Okay, I'm sorry, magnesium oxide. Now, balancing, which we haven't talked about yet, this is how the balancing would occur, but I believe in the next slide we talk about balancing. Here we go, balancing. The equation must be balanced so that the same number of each kind of atoms appear on both sides of the equation. So I just talked about the conservation of mass. However many atoms you have on one side, you have to have the same number on the other side. Okay, so balancing is achieved by writing appropriate coefficients. These are numbers in front. Okay, like for example, if I took H2 plus O2 and said, well, I want this to balance, so let me just write it as H2O2. Yeah, everything's balanced now, right? Well, yes, but this is not water. This is now hydrogen peroxide. By doing a subscript, you actually change the actual our molecule. You change what the statement is saying. So this is not what you do. The way you make equal number of atoms on each side is by putting whole number coefficients. So even though it's not written here, there is a 1 right here. You don't write the ones. Okay, and basically notice I have so I have 4 hydrogens on this side, 2 oxygens on this side. I'm sorry, 4 hydrogens and 2 oxygens. And over here, I've got 4 hydrogens and 2 times 1 and 2 oxygens. So I have equal number of atoms. So this basically is telling me if I want the most efficient reaction between hydrogen and oxygen, I have to always add twice the amount of hydrogen for every oxygen I have. Okay, so if I have like, I don't know, 8 moles of hydrogen and I want a completely efficient reaction, I need to react it with 4 moles of oxygen. All right, if I did any more than 4 moles, then that additional amount would be excess. It would be left over. It would not have hydrogen to react with. All right, and you'd form twice the amount of water. We're going to talk much more about this. It's kind of what we call mole-to-mole ratios in the next chapter, in chapter 11. But for right now, we need to understand how to balance. Well, in this slide, it's important as to why do we balance. Okay, it's based off of the law of conservation of mass and that statement that we said at the beginning, that whatever atoms you start with, you got to end with the same number and the same type of atoms. Okay. So there's a bunch of rules. I'm going to talk about one that is not stated in your book that I think is actually much more helpful. But these are actually pretty good rules like to start with. Okay. So the first one is change the coefficients of compounds before changing the coefficient of elements. All right. My rule. This is saying like if you have a compound and an element. Okay. Start balancing the compound first. My rule is like this, but a little different. I'm going to kind of put, I'm going to add to this. Basically what you want to do is start balancing the molecule with the greatest number of atoms. And I will show you examples once we go to the next slide. Okay, so of all your molecules or atoms inside your equation, find the one that has the most number of atoms and then start balancing with the highest number atom. Start balancing the highest number of atoms. All right, this is kind of a first good rule, okay? Second rule is that if you have polyatomic ions, don't try to balance individual atoms, balance the polyatomic ion. So like if I have, I don't know, lead nitrate, okay, whatever, and I have a reaction and it forms, I don't know, let's say like iron nitrate of some sort, and NO3 2 or something. This will be a 3. Don't try to say, well, I have 3 nitrogens and 9 oxygens. Just balance the actual nitrate itself. So I have 3 nitrates here and like 2 nitrates here. There's obviously more to this problem, but this is just the example, just so you have an idea. And we will see an example of this. Okay, balance the polyatomic ion. Don't balance each individual ion. Okay, and then count atoms and/or polyatomic ions carefully and track their numbers each time you change the coefficient. Okay, there's also another rule where we talk about combustion reactions, and I will talk about that when we get to those type of reactions. It is one of the reactions that we'll have to learn, so I want you to start being able to recognize that type of reaction, and we'll start, right now when we have to balance it. Okay, so let's start with some balancing. Okay, so the first rule I gave you is start with the molecule that has the most number of atoms, and then start with the atom in the highest amount. Okay, so this molecule has 6 atoms in it, 5 chlorines and a phosphorus. This one has 3 atoms. This one has 8 atoms. We have 8 atoms in that one. All right, and then we have 2 in this one. So I'm going to start with the molecule that has the most number of atoms, which is this one, H3PO4. There's 8 atoms. Then I'm going to start with the atom that has the most amount in this formula. Okay, so start with the one that has the most number of atoms, which is this one. Then I'm going to start balancing with the oxygen. And then once I'm done with the oxygen, then I go to the next highest amount in that same formula. Okay, so notice I have 4 oxygens on this side, and I only have 1 oxygen on this side. Well, I have to get this to 4, so I'm going to put a whole number coefficient in front of water to now say I have 4 oxygens. Obviously, this is starting to change my hydrogen count. All right, so obviously I'm going to have to do something here. Okay, then go to the next atom. I've got 4 hydrogens, but notice the hydrogens are in 2 different atoms on the same molecule. That can get very challenging because the question is, do I start changing numbers in front of this one, or do I start changing numbers in front of this one? When this occurs, skip that one and go to the next one. Okay? Only if you have the same atoms in more than 2 molecules on the same side of the equation. Okay, now notice I have 8 hydrogens, so I have to get this to 8. So the question is, do I make this into a 5, or is there somehow I'm going to make this into, I don't know, a 2 to make it 6, and then put another 2 over here? There's so many options, and I don't know quite yet. So if you have more than, now if I did not have a hydrogen here, then I would just balance my hydrogens and I'd be done. All right. So, but in this case, if you have more than one of the same atoms, that's kind of what you want to do at the end. Those are ones you want to do at the end. All right. So then I go to the next one, which is phosphorus, and I have 1 to 1. Okay, so that's balanced. So now I go to the next molecule that has the greatest number if things are not balanced, and that would be this molecule. And then start with the one with the highest number, and that is chlorine. There's 5 here and only 1 here, so I need to put a 5 out in front of here to balance my chlorines. So now I have 5 chlorines, and I've got 5 chlorines. Perfect. Now let's see my phosphorus. My phosphorus, I have 1 phosphorus here, and I've got 1 phosphorus here. Now let me look at my oxygens. This is the last one that my hydrogens. This is the last one I'm going to do. And notice I have 4 and 2 for 8 hydrogens. Okay, and notice I have 3 here and 5 here for 8 hydrogens, plus my 4 oxygens and 4 oxygens. So everything is completely balanced. Okay, if you were to try to balance your hydrogens first, it would be a nightmare. Where do I start increasing? How would I know it's 8? Like I have 3 here and 1 here for 4, so do I just put a 2 there to give you 4? Well, then my oxygens are imbalanced. So then I got to erase that and put a 4 there. Anyone that's ever tried to balance, this is a common theme. You kind of go back and forth and back and forth and back and forth. If you follow this process in this type of a problem, it makes things a lot easier. Start with your highest amount of your molecule with the highest number of atoms. Start with the one with the highest number. Make sure there's not 2 of the same molecules that have the same atoms in it. Okay, you want to do that one at the end. Okay, now down here we have polyatomic ions. Notice I have a phosphate here and a phosphate here. Okay, so in this case you want to balance the phosphates, not each individual atom. So notice I have 1 phosphate here and 2 phosphates here. So that is how you want to do this. So use the same principle. Find the molecule that has the most number of atoms. Count your polyatomic ion as one group. So this has 3 groupings, right? 1 calcium and 2 chlorines. This has 3 sodiums and 1 phosphate for 4. This has 3 calciums and 2 phosphates for 5. And then this only has 2. So I'm going to start with this one. And in particular, I'm going to start with the calcium because there's 3 calciums to 2 phosphates. So 3 calcium here, so I have to put a 3 in front of my calciums. I'm going to erase these now because they don't really mean anything anymore. Okay. Then I go to the next one, the highest amount, which is my phosphate. I have 2 phosphates, so I'm going to put a 2 in front of there. So my calciums are balanced. 3 calcium, 2 phosphate, 2 phosphate. So now I'm going to balance my, now I got to balance what's left, my sodiums and my chlorines. Okay. Well, notice I have 6 chlorines on this side and 6 sodiums on this side. So perfect. Put a number 6 in front of there, and we are balanced. Okay. A lot of people always come to me and say, "Can you check if I have this balanced correctly?" Well, guys, you can check it yourself. If you have the same number of atoms on each side, then you know it's correct. Okay. So if you're ever doing these problems, you don't really have to look at the answer. You know if you have the answer. All right. This is what's called a combustion reaction, which is one of the reactions that we are going to be doing and learning about, but we're going to learn it early just because there's a special way to balance these types of equations. The way you know it's a combustion is you have a hydrocarbon. How do you know it's a hydrocarbon? Because it's a hydrocarbon. It has a carbon and hydrogen. You're reacting it with oxygen, and your products are always CO2 and water. This is a reaction that you're going to have to know and be able to recognize. Okay, so it's only for combustion reactions. So what's the trick? The trick is just start with your carbon and hydrogen. Start balancing your carbons, just start balancing your hydrogens. We're going to balance the oxygen last. And you remember what I said earlier? If you have a molecule that has 2 of the same atoms in it on the same side, you want to balance that at the end. And we're going to do it, the trick is by using a fraction. Okay, so let me just show you. 4 carbons, got to put a 4 here, 4 carbons. 10 hydrogens, I'm going to have to put a 5 here for 10 hydrogens. Okay, my carbons and hydrogens are out of the way. Now I have to do my oxygens. So I have 8 oxygens here and 5 oxygens there. Okay, so this gives me a total of 13 oxygens. Well, how am I going to make this 13? I can't just write 13 because if I write 13, I've got 26 oxygens. Excuse me one second. Okay, so I have 13. I can't just do a 13. Okay, so how do I make this oxygen into a 13? I'm going to use a fraction. It is 13 halves of oxygen, right? Because if I take 13 halves and multiply it by 2, because there's 2 oxygens for every mole, the 2's cancel out, and I get 13. So that is how I can get a 13 here. However, when you balance equations, you can't have fractions. So in algebra, what you learn is if you want to get rid of a fraction, you multiply everything by this number. So you're going to multiply everything by the number 2. So your balanced equation is going to be 2C4H10 plus 13 oxygens gives you 8 CO2s plus 10 hydrogens. Okay, so that's the trick if you have more than one of the same atom on either side and you have only one of them on the other side. And this happens quite frequently with combustion reactions. Now, this doesn't always happen because if this happened to be 12, let's just say this happened to be a 4, and I got 12 oxygens, then I can just put a 6 there and I'm done. I don't have to do this trick. This trick does not always work. It only works when this number becomes an odd number, okay? Or this number, if you want to look at that case. That number is an odd number. Okay, the best way to get good at these is to do practice problems. There's lots of practice problems in the book, and then obviously I will have some sheets. And I believe there are some problems in here, so I will let you do these on your own. Feel free to do these on your own, practice on your own. You can download the slides and you can do these. All right, so I will see you when we come back with section 10.4.